Hello, welcome to the last set of lectures on this grand introduction. This set of lectures is going to look at the effect of soft information. These are optional if you feel that you got enough of a taste of grand with the hard decision. By all means, stay with that. But if you're really curious about how you can actually take into account soft information with Grant, then stay tuned and let's look at these lectures together. So let's start out by remembering how Grant works and that it is a maximum likelihood decoder when you have hard information. Now, what happens when you have soft information? When you have soft information, the whole system becomes a little bit more tricky. And the reason it's a little bit more tricky is because it's not quite clear how you take into account the effect of the noise. Now, there had been some work in the 70s from Hartman and Rudolph looking at how to do a maximum likelihood decoder with soft information. What they do is they have a decoding rule for linear codes, which is maximizing this a posteriori probability. And this is what they find. They look at an a posteriori probability, so that instead of looking at all 2 to the NR possibilities, if you recall, so opposed to looking to all 2 to the NR possibilities, they actually look at a smaller number of possibilities potentially. The way to think about it here is that N is the length of the code and K is the number of bits that were originally in the message. So R rate R is actually given by K over N. Okay, so basically this is R rate R. So what they do is they look at 2 to the n minus k. Now we know from the work that we've done in the previous lectures that of course r is less than or equal to 1 minus the entropy h of the noise in the binary case. Okay, so if R were exactly at capacity, so this was our capacity. If R was exactly at capacity, then actually it would be that 1 minus Hn being C would imply that K over N would indeed K over N would indeed be the entropy of the noise. So at first blush, this looks like, oh, maybe this actually is looking a little bit like the complexity of Grant. But actually it's not the case because they always have to go through all 2 to the n minus k of these, okay? Whereas what we can see is, of course, generally that's a worst case for us, and generally we actually go on average significantly less, right? So we only have to go to the 2 to the nh and when we actually have to go to look at the entirety of, in effect, the typical set, but usually we guess very quickly within the typical set. And in particular, as the signal to noise ratio improves, goes up, then actually the effect of the noise goes down, and therefore the speed at which decoding the correct effect or guessing the correct effect of the noise to lead to a correct decoding occurs is speeding up quite drastically with SNR. And of course, actually this work only applies to nonlinear codes. Not that it matters a huge amount if you look at linear codes, but we're actually working on some applications where it does. This one is not, this other approach is not universal. So this is an interesting aspect here, but we actually want to do something which goes much, much faster and is universal. Okay. So how are we going to do that? The way we're going to do that is not to do the usual approach, which, if you recall from our other conversations about the state of coding, we're not going to be using a code-centric approach. We're going to be using a noise-centric approach, in particular, in the same way that we saw before that random linear codes, which were known to be capacity achieving in the hard detection case, capacity achieving in the case of maximum likelihood decoding with soft information with continuous noise at the receiver, we're going to show that we can use RLCs again. So RLCs strike back, and then we'll show also some very, very simple codes, such as cyclic redundancy check codes, are able to get up to capacity. Okay. So there are, of course, capacity achieving codes. Many of them have a non-maximum likelihood or only maximum likelihood in the limit. But for instance, you can do belief propagation with low density paracheck codes. You can also do turbo codes. You can do polar successive cancellation with certain block lengths long enough. You can do BCH breakout massing. A lot of code-centric approaches will work. But many, except for polar, they're actually are generally not known to be capacity achieving in the soft information case. Okay. So, why are we trying to stay away from the code-centric approach? As we said before, in the case of hard decoding, we don't want to be limited to just a certain number of codes with certain number of lengths, certain number of rates available. And also it would be nice to have a single decoder that is able to manage all kinds of different codes. So we're going to be using the noise-centric approach of guessing random additive decoding. And this is something where we're still going to go guessing from most likely to least likely, but rather than the noise sequence, as we mentioned before, we're really going to be concentrating actually on the noise effect. So that is the big change going really from the discrete case to the continuous case. What we really care about, as we mentioned before, is going to be the effect of the noise. Okay, so we're going to look at the effect. Okay, it's actually highly parallelizable, just as we, oops, excuse me. It's actually highly parallelizable, and it has a variety of other properties that we're not going to go much into. But of course, one of the aspects, as I mentioned before, in the context of the chip, is we would like to have a single system that covers all of the different possible code books. One of the things I wanted to bring up, because there was a question during the question and answer section about this average latency, I want to highlight that this part here is the tip that we have done, given this reference here, Riaz et al. This tip, which will be presented at IESoc in the fall in France, is the one that I'm talking about here. This is some design based on GRAND that has been done but has not been instantiated on a chip. This was done by the group of Professor Gross. Okay, so remember how we managed to do GRAND with abandonment for linear codes? Basically, no matter what the code is, the point of the code is simply to provide a hash or a way of verifying that a candidate code word, which came from subtracting the effect of the noise from the received signal. So here we have the subtraction of the effect of the noise from the received signal. This is now my candidate code word. And all we're really using the codebook for is verification of whether the candidate code word is indeed a valid code word or not. Okay. All right. So we also know from what we've covered before that we can do an abandonment, and indeed, if the number of guesses is getting close to the cardinality of the typical set, we know that we can abandon and still have the system be a maximum likelihood decoder, which will get the correct code word with probably going to 1 for any rate up and including that can get arbitrarily close to capacity. The idea here is that you're better off just not decoding than actually just decoding to something wrong, which is going to take you a lot of energy to decode and is not actually helping you in terms of your performance in any considerable way. All right. So let's revisit our GRAND algorithm. Remember, we have that you have a certain number of tries, and until the number of tries does not exceed your bound for abandonment, you keep going from most likely to less likely putative noise. You subtract the effect of the putative noise from the received signal. You then, in the case of a linear code, using this matrix H just to, in effect, verify whether the the possible code word is indeed in the code book. So this, if you've taken any classes in coding, you will often see described as the syndrome. Okay. But the way we're using the syndrome here is rather different from the way the syndrome is often used in many systems. The syndrome is computing and then decoding is done on the syndrome. Here we didn't compute the syndrome from Y. We don't compute H of Y per se. All we really care about is whether the syndrome of the candidate code word is indeed 0 or not, where a 0 syndrome indicates that the candidate code word is indeed a valid code word. When the valid code word is found, that is a maximum likelihood code word, it's found. Otherwise, you increment the counter if you haven't gone past the bound, and you start all over again. You keep going this way. If, of course, you exceed the bound, of the number of guesses, then in this case, with abandonment, you go ahead and declare failure. All right, so what's a little tricky about having the soft information? Well, what's tricky about the soft information is that when we were doing hard information, in effect, what we had was we were just having a line here that was going, say, if I'm using BPSK, binary phase shift keying, or +1 or -1 are equally likely, and I'm putting lines here at 0, I'm just eyeballing it. What would happen is, see, this one here is very, very close to 0, but we really didn't distinguish between this case where you might just be, a tiny, tiny little amount to the right of 0, in this case where you're a healthy amount to the right of 0, or this case where you're even beyond the +1. All of these would actually all map to a 1. Then, of course, the decoding would try to correct, but without the assistance, without the help of knowing where the received signal actually fell in this real line that I'm showing here. Okay. So how do I take into account this information, but without having to do the naive thing? And what would the naive thing be? Well, the naive thing would be that I would, have some sort of really fine quantization of all the possible values that were received, and that I query along a quantization here to see, what the different possible noise effects were. Was this a noise effect? Was this a noise effect? And so on. Clearly, by the way, that would work. Clearly, by the way, also, that would not be an attractive notion. Why? Because then my complexity, rather than just going as to the NH, N would be going as to the NHN times the quantization. And so the complexity would be exponential with the quantization, and it would not grow in a way that would be in any way attractive. So that's not what we're going to do. We're only going to take into account the fact that what I really care about is, to some extent, what is the extent of the noise relative to each other, not really the absolute value of the noise. Remember, even though we're doing noise-centric decoding, we're not actually interested in the noise per se. We're really interested in its effect. There are a couple of approaches to that. One, which I'm not going to cover, but you can find here the reference that we did with Ken Duffy, is to look at symbol reliability. It uses 1 bit of soft information per channel use. You just see whether the bit is reliable or not. If bits are reliable, you don't guess on them. You assume that the noise has been 0. This actually turns out can be very positive in terms of complexity, because of course now you only guess over the noises, the noises over which you're uncertain. We obtain also a very interesting result, in the sense that you can decide the type of reliability that you're interested in, and therefore you can always set the reliability to be such that it matches your block error rate requirements. And of course, if you basically only look at the most reliable bits as not being in play, then actually you can match that block error rate. So you can take all those into account, and there's some interesting things to be done, but there's too much to cover in this course, so we're not going to do that. There's another approach, which is called OrbGrant, and actually OrbGrant is an extremely good approximation of SGRAND that we're going to see here. I'll show you OrbGrant results in the last lecture. that approach, which was developed by Ken Duffy and just presented very recently at ICASP, uses log2n bits of soft information for channel use, and it queries the vectors with respect to logistic weights. So it assumes a certain behavior of the statistics of the noise, and it turns out that for additive white-Gaussian noise, it has a staggeringly good match to the full soft information, which is what we're covering in this lecture. I won't cover OrbGrand in terms of algorithmic development. I encourage you to look at the reference, but I will show you later some of the results with OrbGrand, in particular compare them to SGRAND. So what we're going to look here is at the full SGRAND. Okay, so we're going to fully use the soft information. We're still going to be fully ML. We're going to allow any kind of code. This approach is suitable for memoryless channels. So remember that when we had hard detection, we were able to do some interesting things when there was memory. Here we're just looking at memoryless. And it's suitable for moderate redundancy codes. That's to say, codes where the rate is relatively high relative to the length. I'll show you later in the second part of this lecture what we mean by moderate redundancy codes. It's not short length, is not high rate. It's actually a region of rates and lengths, but really what's fixed is the redundancy. We just don't want a whole lot of redundancy, which in effect means that we want to have codes which are generally working well for ultra reliable low latency communications. Okay, so how does this work? So I have my code word, it's modulated, it's transmitted. This is the proverbial X that goes through the channel. The channel has some effect, produces the Y, and if I had the hard demodulator, I do grand the way we've seen in the previous lectures. But now if I don't hard demodulate and I have the Y directly, I'm going to do SGRAND. Okay, the assumption is that the a priori demodulated probabilities are equal. So we have something which is very common with current modulation schemes and also current coding schemes, and would also be the case with other uniform coding schemes such as random linear codes, which right now are not used because up until now there was not a proper decoder. Okay, and we remember that the demodulator, the decoder would still be basically the search, the maximum likelihood decoder would be the search for the argmax of the input that maximizes the a posteriori probability of the observed output Y. Okay, so how are we going to manage this? As I mentioned, we're not going to try to slice things up and do the naive thing of having just a quantized noise. We're going to use an ordered error indices vector. Okay, I want to just highlight this a little bit. Why is this important? Well, this is important because it's really looking at the effect of the noise, okay, which is basically for different ij's and different y's. This is basically this ordered index vector is unique almost surely for continuous memories channels, okay? And in particular, if I look at this OEI vector, then basically what I'm going to do is that if I look at the J star, that's mean that this maximization one, it's going to be 0 if the noise happened to be 0, so there was nothing happening. Another one, it's going to be the noise effect that's going to give me this this max. Okay. Now, why did I need that memorousness in the noise or the channel effect that I mentioned? Well, here it's where it shows up. Here is where it shows up. Okay, I need to have that these I'm going to be needing to have that these noise aspects are going to be multiplicative, so that I'm going to be able to do some sort of order of this type. Okay, so basically what's going to happen is, suppose I have this noise here is 1, 0, 1, okay, and then J is 3, then I have to be able to have parents, and I need to be able to have children. Let's look at a little example here. Oops. Okay. Basically, what's going to happen is I'm going to be able to have some sort of parenting or, structure here where I have 0, and then I have all of the other noises that could happen be ordered in some sort of tree structure. Okay. And if I go all the way up from a leaf, all the way up this tree structure, I have to get to the 0 vector. Okay. And once I have this tree structure, then this is actually going to streamline my search. So what am I doing? Let's look at this algorithm, which mirrors the GRAND algorithm that we saw before. So I'm still going to go through all these trials until I abandon, until I reach some bound B. What I'm going to do is I'm going to have a putative noise here, which is going to be my theta y minus v. So it's going to be this argmax for this theta y minus v. And then if this was indeed, once I take this demodulated, I take out this noise effect, if that's indeed in the code word, then I know that this is a maximum likelihood code word. If that wasn't the case, then what I'm going to do is I'm going to change the set cal s here. I'm going to then take out the e. I'm going to instead replace e with its children. So I'm going to grow it here by taking out e and replacing it with its children. And then I'm going to start over again. Okay, so I'm going to be doing this over and over again. I'm basically just traversing this noise tree by going all the way down basically through the children. So starting with the top of the tree, which was E equal to 0, and going down. Okay, so basically just to give you some idea, here I have these different probabilities, P theta yi given yi is 0.6, etc., etc. So these probabilities are the ones that came from the soft information. Okay, and suppose here basically what I have is I have these following probabilities. These are actually the possible inputs that could have been happening. The possible the different this is the demodulation given the y3. Okay, and what's going to happen here is I'm going to be starting over here, then going to 2, then going to 3, depending on the value. I might then then I go to 4, then I might go to 5, then I might go to 6, 7, and 8. In some other examples, I actually will go 1, 2, 3, 4, 5, 6, 7, 8. Okay, it's going to change according how I traverse this tree is going to depend, actually have two examples, the blue and the red. It's going to depend on how we're doing the um, soft information. Okay. There are two things that you can show here. The first is that you'll always look at error effect vectors, guessed in non-increased error order, and therefore you have that the return code word is ML. The second one is that you do have progress. Each error vector is guessed at most once, so you're not going back and doing the same thing and over again. And you can show this by an induction on the number of guesses G, okay? The base case is easy. It's you were here, you had one unique child. And the induction step is the noise effect that's guessed means that the parent had been previously guessed, and therefore you're not guessing it again. Just to give you an idea of how you're doing the guesses, this is for both Chaudhary-Hockenheim code and also for random linear code. You see the exact same type of guesses, and these are basically the way to think of these is that this is the length of the code. This is where you guess that say there was a flipping of the bits. And you can see basically how many, sorry, the other way around. You can see basically how many you can see this is how many bits were flipped on the bottom. Sorry, this is how many bits were flipped. And you can see how often those are occurring. So you can see that most of the time no bits are flipped. And then some of the time you get 1, 2 flipped bits, and then very few times you get more bits flipped. But I'll show you another picture later, which actually, rather than describing this one, will make things a little clearer. And here it is. So what happens with hard decision, Grand? You can see here's the number of queries, okay, which was basically what we were showing here in terms of number of queries, okay. This is the query number, and this is, you know, how many times you basically look at one error. This is how many times you get 2 errors. This is basically where you finish. If you have soft information, in this case, by the way, again, it's a BCH code. You know the minimum distance, the dmin of the code, which normally is giving you a limit to how many errors you can correct. And what you can see here is that with soft information, you can actually keep going, fall below this limit, and you can decode for Hamming weights that are much, much higher, okay? So what you're seeing here is also the query number. This is the number of bit flips. So this is, you know, the first query sees only the most likely bits being flipped. The last queries see more bits being flipped, but basically you can see these are the number of, this is from the most likely bit to be flipped to the less likely bit to be flipped. There are of course more bits than that, but we're not showing them here because in practice they never get flipped. So think of this as being the 60 most noisy symbols, the 60 most noisy received bits. What you can see here is the picture of how the bits get flipped. And you can see that very often you'll have multiple flips, and you'll have sort of these little holes here where you're actually more likely to have had somewhat more a less noisy bit be flipped than other and along with very noisy bits being flipped, rather than just having medium noisy bits be flipped. So that's very interesting. See the noisy bits being flipped, the medium noisy bits being flipped happen sort of over here, and as you go forth, you know, you sort of foraying further and further away into the less noisy bit. So I want you to think of this abscissa as going from least noisy bit to most noisy bit. So it's a very interesting way of representing this. And we ran this for BCH RLC. You have exactly the same pattern. Why? Because again, we're not noise centric. We're not code centric. We're entirely noise centric. Therefore, the code being a BCH or RLC really does not matter to the decoder. Okay. Another way to look at the same data, visualize the same data, is that here I'm looking at the cumulative distribution function for different Hamming weights of the noise. And you can see this is noise of weight 1, weight 2, and then by the time I get to 5, 6, 7, 8, it's getting very close to 1. But again, how this weight happen doesn't mean that it only happens among the most likely likely to be flip bits. It doesn't just happen among the most noisy bits. It actually happens with some interesting gaps in between which bits are flipped. So it's a very, very interesting behavior. Okay, so how does this soft grand with abandonment work? So at each iteration, my cal S only grows by most 1, right? Remember, I'm replacing cal S with its children, okay? So if I'm removing the noise if I just looked at, I do union with the children. So it's growing by at most 1 per time because per run because it has 2 children. And at each iteration here, what I'm doing is I'm extracting the most likely noise sequence, I'm performing matrix multiplication, and I'm adding almost 2 noise sequences. One of the ways, by the way, in which we can implement this is as a max heap. I'll go back a little bit later and show you a bit about max heap. But why am I doing this as a heap? I'm not actually needing to order all of the noise sequences from the beginning. I just need to have a heap structure rather than a fully ordered structure, because I just need to make sure that items that are at a certain level in the tree are more likely than items that are at a lower level in the tree. I don't need to have a full order. This is one of the things that sometimes when I'm teaching introductory sophomore class in algorithms, I like to describe as trying to arrange people for a race. All you need to make sure, you don't really need to make sure that when you have your runners start in a race, you're going to have the fastest in front, the second fastest, and so on and so forth. All you really need to make sure is that you arrange people in a race in groups so that one group isn't going to have to overtake the other group and create chaos, right? So in races, in road races, people get arranged by roughly how fast they run. It's the same thing here. You don't really need to arrange in such a way that all the noises are perfectly arranged with respect to each other at the beginning. You just need to have a heap structure, okay? So the complexity is then going to go with the number of guesses, G. We have log of G, of course, we have to be able to represent G. We have the Maltese multiplication, which we're noting here by F and K for this matrix multiplication. And the worst case complexity, therefore, is going to be when G hits B. On average, however, it's going to be significantly lower. And as SNR improves, it's going to improve very significantly. Okay. Let's just go ahead and take a look at what this looks like. Here we have, we'll revisit some of these types of results in a little bit. Here I have, say, binary phase shift keying, so the kind of +1, -1 signal that I showed you in an earlier picture. And here you can see SGRAND and with an RLC. you can see SGRAND applied to a CRC-aided polo code. And here you can see the state-of-the-art CRC-aided successive cancellation list decoder with a list size of 32. So typical chips will actually have a list size that's smaller than this. So this is a very generous list size. And another thing to recall is that the complexity of these CRC-aided successive cancellation list decoders for Polo codes, actually the complexity grows exponentially with the list size. So a list size of 32 is actually leading to a fairly complex decoding. And what we see here is that we're getting a very big gain, okay? And also what we see is that it's okay, this erasure rate here is basically how much we have to abandonment. So you can see the abandonment does not in any way dominate the error. So the dashed lines here, we to think about them is this is the abandonment rate. So the abandonment rate is not impacting, really, it's not dominating the error. And what we can see also here is that the SGRAND with the block error rate or the SGRAND with the zero polar give very similar performance. The RLC is actually a little better. But basically what's happening is that we don't care what kind of code we decode. Here's a little example to show the effect that I mentioned before, where the average is much better than the worst case. So you can see here's the average. And here, by the way, is the median. And we're doing a little bit of simple statistics here, but you can see the average is generally much better than the worst case. And also you can see that the complexity in terms of number of queries improves quite steadily with the signal to noise ratio, right? So when the signal to noise ratio here is around 5.5, let's say 5, which if you were using the state-of-the-art decoders, we would be getting a block error rate here of about 10 to the minus 3, but if you were using SGRAND, you would be getting at 10 to the minus 4, you would actually be getting an order of magnitude improvement in block error rate. And so if you look around 5, you know, the average here number of queries is a few hundred, which is really not bad at all because the code itself is 100. So you're really getting just a few queries per bit. It's a linear complexity, and in fact, it's quite low. So you can see the same sort of behavior here. Again, this list size of 32. Just want to highlight it. What you can see is that, again, we do better than the state of the art, or what's somewhat better than the state of the art. Again, as I said, 32 is a very generous list size. Whether you're using a CA Polar code or you know, it doesn't matter so much. Here, what we see is different abandonments. This is all CA Polar codes. We see different abandonments. We can see that the abandonments really don't matter much. As a matter of fact, if you increase if you decrease your abandonment, so give up more quickly, you know, you actually get a slightly better behavior. Why? Because you don't end up hitting a wrong answer. This is an illustration of a phenomenon that I mentioned earlier in the class, where if you have guessed a long time, it means that you have an unusual noise. It means that you're running a higher risk of having an error, and therefore you may actually benefit from just giving up when things are not going well. You know, it's a wise person who just says, never mind, I'll just give up. And you're seeing that effect right here. You're seeing that effect right here. okay, where you're seeing a slight improvement by having an upper bound on the abandonment here that has changed, okay? Okay, anyway, so what does this give us? It gives us an ability to decode a variety of codes. We saw some RLCs, we saw some ECHs, we can do pretty much any old code we want. And I just wanted to, before I start this lecture, just show you a few more results and then maybe remind you a little bit, as I promised I would, about heaps. Okay, so again, these kinds of behaviors that we see are very, very consistent across a very large number of codes and weights. So here's binary phase shifting. By the way, the curves we saw just before this were QPSK. I have here polar codes. I have here just using a CRC, a Bose-Chaudhuri-Hockenheim code, a random linear code. Anything pretty much works. The only ones that don't work so well are the polar codes. The polar codes by themselves don't work well. The polar codes with a CRC added to them, which is the red line here, the CA stands for CRC aided. Those actually work, those work fine, but it's not clear if it's because of the polar code, because the polar code doesn't work so well, or it's just because of the CRC, because the CRC works pretty well. Random code works very well. I want to highlight actually that when I talk about a random code here, this is not a search over different random codes. There was a question about this in the previous Q&A. This is actually the first code picked out of a hat. So when we're saying it's random, it is random. It's not fancy. It's not a random search over a set of codes. Okay. And what you can see here is again RLCs, CRCs, here BCHs, BCHs and RLCs do very well. The CRC here is not quite as good, but it's but the same as this RLC. The reason you have these two curves here is because you have somewhat different redundancies. So here you have a somewhat lower rate code here for the blue and the turquoise, and here you have a somewhat higher rate code. So of course, as your code rate goes up, so does your block error rate, but very likely. Okay. I just want to go very quickly over maybe going a little bit over this example a little bit. So remember, I have these different trials here. So here is the case for the of running the algorithm. So remember, I start with all zeros. Okay, that is actually my initial set, and this is corresponding to having no noise effect. I have a probability associated with that. My J star in this case noise is 0. I check. I go through if it didn't happen, if that wasn't all zeros, then goes to the next one, which in this case is going to be now, look at J equal 2, I'm going to 1, 0, 0. That didn't happen. I then go to the next one, which might be 1, 1, 0. I add every time I'm going through the children. And so I just wanted to show you how we're growing this, okay, until we get to the ML code. And a max heap, remember that it's a data structure that stores n elements. And as I mentioned before with my example of setting runners up at the beginning of a road race, it's simply a system where every node has greater values than its children. So if you just don't want people running into each other, the root has a maximum value, but it doesn't mean that this node over here is in any way greater or lesser than the node over here. It just means that collectively these two nodes are not going to be greater than their parent, okay? And this is the max heap. And this is, of course, all that we're using in our algorithm, okay? Why is max heap pretty nice? Max heap is pretty nice because I can heapify, have this order log n to maintain the heap property. So basically, suppose that I have to extract the maximum. So in this case, what are we doing in our system? We're extracting the maximum. I only need order log n, okay? So finding the maximum is order 1 because it's always at the top. And then reordering my heap to make sure that my heap works fine is called heapify. Again, if you do sophomore or junior level course in algorithms, you will learn this. And this is actually where that log n comes from in our algorithm complexity. Adding an element, by the way, is always just order log n, okay? And remember, I'm adding an element here when I am adding the children. I'm adding an element, okay? That's order log n in a heap, okay? And therefore, this is what gives the order log n in my complexity that I showed you before. Okay, so that's where this log n came from. All right, so with that, I think we've covered soft grant, and particularly what I want you to remember is this structure, this heapifying aspect to it. This is not a bad complexity. It is basically, polynomial in B. And B is a bound that we pick. But actually, we're going to see some other practical ways of doing self-decoding in the next lecture.